All right, welcome back. Yeah, so it turns out we've got the pandemic on the go, and now the power's out at the house. So lots of fun going on here. Maybe I've got some juice left in this iPad, so I can get another lecture in here. What we're going to talk about is a new type of series, and it's going to be different than the previous series we've considered because most of the other things we've considered are assuming that the terms in summation of an, we typically look at these things and we make the assumption that an are positive terms. Okay? And we often bound them above zero and so on. We're going to look at a different feature of series that tend to arise very frequently when we actually use series. And what I'm going to do is introduce a couple of building blocks to these series. So let's consider, first of all, this summation here. Sum n equals 1 to infinity of negative 1 to the n. All right, so I just want to write out some of these terms. When n equals 1, of course, that's negative 1 to the 1, and then I have the next term as negative 1 squared, and then negative 1 cubed, and negative 1 to the 4th, and so on. And now when I write these terms out, the negative 1 to the 1 is just negative 1, but then when I take negative 1 and square it, of course, I get positive 1. So it goes plus 1, and then multiplying again that term by negative 1 becomes negative 1, and then positive 1, and negative 1. And it continues in that fashion, alternating from negative to positive for all the terms to infinity. Similarly, I can write n equals 1 to infinity of negative 1, and I'm just going to change it slightly to n minus 1. And when I do that, I get negative 1 to the 0 plus negative 1 to the 1 plus negative 1 squared plus negative 1 cubed, and I keep moving up. And this is identical to the previous series I've written out, except that the terms, the first term in this is a 1 instead of a minus 1, and then it alternates to a negative 1, to a positive 1, negative 1, and it continues on in that fashion. So if we want to take a series and turn it into something that alternately goes positive, negative, then we need only introduce these little negative 1 to the n or n minus 1 terms. And which one you choose depends on whether you want your first term to be positive or first term to be negative. Okay, so those are the building blocks to these new type of series. And now I want to consider an example series. So we'll go n equals 1 to infinity. I'm going to go negative 1 to the n minus 1. So first term positive, second term negative, and so on. And I'll go over n squared. Now, if I was to write that out, the first couple terms, I get a 1. That would be negative 1 to the 0 over 1 squared. Minus a quarter when n equals 2. Plus 1 over 9 minus 1 over 16. You probably noticed the pattern now, and that continues on and on and on. All right, now in the back of your head, I want you to think about this series. Just consider it for a second, 1 over n squared. Okay, this is a p series with p equals 2 bigger than 1, and I'm expecting convergence. Or not expecting it, it does converge. 1 over n squared does. All right, so keep that in the back of your mind. I want to go back to this fellow over here. Okay. And just like I did with the integral test, I'm just going to draw a picture, and I want to draw these rectangles that kind of represent the areas as I go off through these series terms. All right, so what I'm going to do is draw to the best of my ability. Oh, settle down, pup. Dog's jumping around there. 1 over n squared and negative 1 over n squared. It's something like that. Not perfect, but whatever. And I'm going to mark off 1, 2, 3, and maybe a 4 in there. And I'm going to draw these rectangles. So the first term is a 1 in this series, and I just want to represent this as an area. Okay, now 1 over n squared is just giving me the function height, which is part of my series term here. Okay, right in there. So the first term is a 1, and that can be represented as that area right there. Okay, I'm going to draw it in as a 1. Right there. All right, now we're going to move along. We're going to continue on with this process. Now the next term is a negative 1/4. So again, I'm going to use the function 1 over n squared, but it's negative now. So now I'm going below the axis over to here and up. All right, we have this area. And this area is, wrong color. That area is negative 1/4. Okay, now we continue on the same approach. We have this area in here. That's positive 1 over 9, where n equals 3, so we have 1 over 3 squared is 1 over 9, and then the negative 1 to the power 2. 2 gives you the positive term. Okay, we'll do one more. It's getting very skinny in there, but at the fourth, in there, that little area is equal to negative 1 over 16, and you can see it just continuing on and on like this. All right. Now, remember when we did this for 1 over n squared? That's the same picture that I drew here, except all of the areas are above the axis, so they're all going to be positive quantities. Now, in this case, I'm taking the 1 over n squared, this thing that I've already looked at and I know intimately, its convergence. And now I'm taking half the terms and I'm putting them below the axis, and now I'm adding all those terms up. So, we're essentially asking this question. If I know that taking 1 and then adding a quarter and adding a ninth and adding a 16th and adding a 25th and continuing on like that equals something finite. Okay, I think this converges to 2, but it equals something finite. Now I want to go and look at something that is similar to it, but it alternates positive, negative, positive, negative. 1 minus a quarter plus a ninth, minus 1 over 16, plus 1 over 25, and so on. If I know that this first statement is true, that this is something finite here, then I want you to think about for a second, can I say anything about this expression here? Okay, so think about that. What can I say? And so I hope, if you think about this for a minute, the first one being something finite, if the second one is the same as the first one, except every second term is negative, I get this extra kind of cancellation effect. Or up here, I get the positive areas and the negative areas, and then the positive area and negative area. Those will kind of cancel out as I sum them up to infinity. And that cancellation effect would make the stuff in green down here, you'd expect that that would kind of converge more easily in some sense. And so if you have all the positive terms converging, summing up to something finite, then if I alternate the series, I must also get something finite. And it's going to be less than the thing in the blue box because of all that positive-negative cancellation that happens in the total sum. All right, so I'm going to write that little observation that might feel intuitive, and I'll just write it in the kind of the standard mathematical way that we do things. And I'll say this. If an, the term that describes my series, contains positive and negative terms, and the series that is represented by only looking at the positive values, and the equivalent of that consideration is this thing, looking at only the positive analog of the series we're considering. Okay, so if that thing, if the absolute value of your ANs, okay, gives you a series, and then that series converges, so does the series that contains both positive and negative terms. And it's all back to this fact that the cancellation effect makes it easier to converge in some sense. Now, this is an example where I've got here the blue box and here the green box of two series where the absolute value right here, this is like the absolute value of an, that converges. And we saw that that implies that the regular series an converges. Okay, so this an here, that converges. So in some cases, we have both the absolute value of the series and the alternating positive, negative series. They're both convergent. And we've got a name for that. Okay, so I would say, that's one little point. I would say if the summation of an converges, where an is an absolute value, that's the hard one to get to converge. It's harder than the one that has both positive and negative terms. But if that one converges, and the sum of an converges, now it must if the absolute value converges, so you really only have to show for the absolute value. But if they both converge, we say that the summation of an has absolute convergence. So it's a very strong form of convergence. It means that even when I take the absolute value of the series, turn all the terms positive, that will still converge. 1 over n squared in the previous example. Now, that's not always the case. Because the absolute value of the series has all positive terms, but the alternating positive, negative type series, or any series with positive and negative terms, has a stronger ability to converge because of that cancellation effect that we've been drawing up here. The positive and the negative parts are going to balance out somehow. Then it leads to another possibility that we have to keep our eye on. And I would say this. Okay, this is the other possibility. The summation of the absolute value of an, if this one diverges, but the series itself, which has positive and negative terms potentially, converges, because of maybe you got some extra convergence property from that balancing effect. Okay, we say this an has conditional convergence. So those are two new terms: absolute convergence and conditional convergence. All right, so I'm going to try a little example here. Okay, so let's consider. Again, we'll keep it nice and straightforward and simple. N equals 1 to infinity. We're going to make this have that positive, negative structure, n minus 1 over n. And again, I'm going to write out the first couple of terms of the series. They just go positive, negative, and n just increases the numerator. So I have 1. Next term is negative, a half, plus 1/3, minus a quarter, plus 1/5, and it continues on and on. We want to look at this from a point of view of absolute and or conditional convergence. All right, so the first thing I can do is take the summation of the absolute value of an. Now, all that does is it takes the negative 1 to the n minus 1 term, which is positive 1 or negative 1, and when I take the absolute value of that, I simply get 1 every single time. So that is, if I take the absolute value of this series, I simply get the sum n equals 1 to infinity of 1 over n. Now, you could either use the integral test, we've used that before, or you could just remember that this thing is a p-series, but we know the convergence. The p-series, p equals 1. And if you remember to our rule, p equaling 1 indicates divergence of the series. All right. So right away, we know that this series up here that I started with, underlined in the green, that series does not absolutely converge. If we took the absolute value, we ended up with a series that diverges. Now, I'm going to take these terms here, pull you down, and even though when I take the absolute value, the series diverges, I'm looking at these terms and I say, well, hey, there's still probably a chance that this thing still might converge for me because, again, this principle of all the positive terms here, 1 and a third and a fifth, balancing out with the negative half, negative a quarter, negative 1/6, and so on. So maybe that cancellation effect is going to still push this series into convergence, provided I don't have the absolute value on the thing. So my little observation here, just to kind of guide my thinking, is I expect it still may converge. I don't know that, but it still may converge due to cancellation effects. Of the positive and negative terms. All right. Now, I don't know what to do with this. I don't have any tests built up for this kind of series. So what I want to do is I want to name this type of series, and then I want to develop a little test for dealing with it. We want to apply that test to this instance and see if we can make a conclusion. And so it turns out that alternating positive, negative type series are given a name that matches that, and they are called alternating series. So these series are called alternating series. And we would write it in the form of negative 1 to the n, an, or negative 1 to the n minus 1, an. Something like that. Okay, they're called alternating series, and the test to evaluate the convergence or divergence of an alternating series is called the alternating series test. So we're going to continue on with our numbering here. We're up to number 6 in our series of tests. Not the final one, but we are getting there, and this is called the alternating series test. So an alternating series of one of the above forms, and I'll write them out again. It could be negative 1 to the n an, or negative 1 to the n minus 1 an, converges if some conditions are met. Now, first thing I want you to notice before we get to these conditions is the structure that I'm writing my series in pulls off the part that alternates, that makes it alternate. So here, this negative 1 to the n, or this negative 1 to the n minus 1, is assumed to be in the expression, and then everything else is considered in this test to be the an. So I don't take the entire expression and call it an, it's just the part that doesn't alternate. That's what I'm labeling an in this test. So it converges if, all right, two things. The first thing I need to show is the terms have to get smaller as n gets bigger. Okay, and you can see I've bounded them above 0, and you might think, well, you just told me they go positive, negative. But remember, it's the an that is the non-alternating part. So all of those terms should be positive, and then the thing that makes it go positive, negative is in the negative 1 to the n or n minus 1 terms, and that's what makes it go positive, negative. But just looking at that an, we want those terms to be positive, and then as I increase my n to be larger, then the term should be smaller. The an plus 1, the successive term should be smaller than the previous term as n increases. That is to say, it's a decreasing sequence of terms. That's the first thing I need to show, and that's usually pretty easy to show. All right, so let's go to the second thing I also need to show. Not only do the terms have to decrease, the an terms, but the an terms as n goes to infinity must also go toward 0. They can't go off to some number like 1, because then at the end of this series you'll have plus 1, minus 1, plus 1, minus 1, something like that. Okay, so the terms have to decay to 0 as well. But if you can show those two things, that's all you need for the convergence of an alternating series. So it's very, very easy to use this test. You simply go to an alternating series, you recognize it immediately from the character of this minus 1 to the n or minus 1 to the n minus 1. You grab everything else, you call it an, and you simply run two little tests on an. Is the successive term smaller than a previous term? Are they decreasing? And are they decreasing to specifically 0? That's what I need to show. All right, so I'm going to apply this to the example I just worked on up above there. And that is, does the summation n equals 1 to infinity, negative 1 to the n minus 1 over n, okay, this example I've been considering, does this converge or diverge? That's my question. We've already shown that it does not absolutely converge because we took the absolute value, we got 1 over n, p was equal to 1, it diverged. Okay, but we still have a chance here of just the alternating series itself converging. So I look at this and say, oh, it's alternating. So try the alternating series test, AST. So I want you to look at that, and we're going to say let an equal, and remember I go up to this expression right here, and I call an the whole part of the expression that does not include the negative 1 to the n minus 1, or negative 1 to the n term. So an in this case is everything else, which is just 1 over n. All right, so I've got my an here as 1 over n. I got to run that through two tests. They're usually very, very easy. And so I check the first thing. All right, so I check, is an plus 1 less than, I don't know if it is, but is it less than an? Are the terms decreasing as n gets larger? Well, an plus 1, if an is 1 over n, an plus 1 is 1 over n plus 1. And so I'm checking, yeah, of course it's less than 1 over n. So I would say, since 1 over n plus 1 is less than 1 over n, that condition is satisfied. And there doesn't need to be a lot of talk about this. I mean, it's just obvious. If I make the denominator bigger by 1, the expression is smaller. So condition 1 trivially basically is satisfied. And then the second thing, also not too much of a challenge. I simply need to go do the limit as n goes to infinity of an, which is the limit as n goes to infinity of 1 over n. Now as n goes to infinity, 1 over n goes towards 0. So equals 0. That's the second condition satisfied. And there's not a lot more I can do except simply state those two facts. And so now I have, so by the alternating series test, that is the AST, this series, negative 1 to the n minus 1 over n, converges. The two statements were shown to be true. Now, because we've already looked at the absolute value of this term, of this series, and showed that that leads to a divergent series, we're going to make a little note here. Note, this series only conditionally converges. Not absolutely, because the summation of the absolute value of negative 1 to the n minus 1 over n which was just the sum of 1 over n, diverges. Okay, so this is an example where we have what we call conditional convergence, not absolute convergence. If I changed this example starting off, if I put a power 2 there, then that would be absolute convergence because the absolute value would be 1 over n squared in the an term. And we've just shown that one to converge whether the terms are all positive or whether they alternate. All right, anyway, conditional convergence.